Hello and welcome to lecture 7. So in last week we were discussing about introduction to axial flow compressor. We have discussed about various applications. Those are related to aircraft, land based power plant. We have discussed about the industrial applications. Then we were started discussing about the construction of axial flow compressor. Now with this detail we moved forward by using our fundamental equation, that's what is called Euler's equation. We have discussed about various velocity components and what are the uses. Then most importantly we have correlated our diffuser or diffusing section or diffuser, that's what is related with our flow passage within axial flow compressor blades. Okay. Then we have started discussing about this process of compression on TS diagram. We have discussed very important parameter called adiabatic efficiency and polytropic efficiency, and we have realized like adiabatic efficiency, that's what is related with the overall stage of the compressor, and polytropic efficiency, that's what is individual stage. Now all these things what we have learned, that's what will be making the base for us in order to move forward. Now again and again when we will be moving ahead, we will be using Euler's equation, we will be using velocity triangle, and this velocity triangle, that's what is most important thing in order to realize what is happening within your axial flow compressor. Now in order to understand what all are your adiabatic and polytropic efficiency, we have taken one tutorial session and I had given you the assignment part. Just have quickly look for that. So this was the problem. It says my industrial axial flow compressor which delivers the pressure ratio of 7.36. It is proposed that the individual stage they are having different pressures here. So it is 1.6 to 2.3 respectively, and their polytropic efficiencies are 80%, 75% and 79%. So you can realize what numerical we have solved in last session, they are having same pressure ratio and same efficiency, polytropic efficiency. Here in this case we are having polytropic efficiency and pressure ratios to be different. That's what will be giving you some different flavor. So what you need to do is you need to calculate your overall efficiency from the resulting stage, and then it says what need to be your polytropic efficiency of the last stage in order to have your overall efficiency to be 78%. Assuming first two stages are as it is, means their pressure ratio and polytropic efficiencies are same. So I had given you the hint in order to solve the numerical. What it says, in order to solve your first case, we are having our overall pressure ratio. So based on that we can calculate our temperature ratio for individual stage, and we can calculate what will be our efficiency, overall efficiency. Okay. Same way second numerical or second case, it says we are given with overall efficiency, we are given with pressure ratio of two stages and their polytropic efficiencies. Now for the same configuration you need to calculate the efficiency of the third stage, okay, and for that it says you are about to achieve your overall efficiency of 78%. So let's move ahead. Suppose if I consider these all are my given data, so I say pressure ratio is 1.6, my polytropic efficiency of first stage is 0.8, my pressure ratio of second stage is 2, polytropic efficiency is 75%. Pressure ratio for the third stage is 2.3 and my polytropic efficiency is 0.79. Now as we discussed, we can calculate what will be our stage temperature ratio for the individual stage using our fundamental equation. So it says these are my temperature ratios for stage 1, stage 2 and stage 3. Based on that we can calculate our overall temperature ratio for all the three stages. We know what is our total pressure ratio for all the three stages, and based on that if I will be putting, I can calculate my overall efficiency including all the stages. So that's what is nothing but in sense of overall pressure ratio and overall temperature ratio. So if I am putting these numbers, it says my overall efficiency, that's what is coming 76.40%. So this is what is giving you idea like what all will be the impact of different pressure ratio and different polytropic efficiencies. Very interesting case, that's what is with say case 2. For that case, what is given, say we are given all these numbers, pressure ratio for stage 3, that's what is given to us, that's what is say 2.3. Now what we know, my overall pressure ratio, that's what is remain same, it is 7.36. So based on that I can calculate what is my overall temperature ratio. Okay, so my overall temperature ratio, that's what is coming 1.985. Okay, now what we know, my overall temperature ratio, that I can write down what is my temperature ratio of stage 1, temperature ratio of stage 2, and what is my new temperature ratio, because now I am looking for my efficiency, overall efficiency to be some number, and for that we don't know what is our polytropic efficiency. So what we will be doing, we will be calculating our overall temperature ratio based on this relation. It says my temperature ratio for the new stage, that's what is coming, or the third stage, it is coming 1.306. Now if we know this temperature ratio, now I can calculate, I can use my relation for isentropic efficiency, that's what is in sense of my pressure ratio and my temperature ratio. If I will be putting this number, it says my efficiency, it is coming 87.80. Now you can understand, when we are looking for our efficiency to be on higher side, say when we are looking for our efficiency to be increased from 76.8 to 78%, one of the possibility for us to increase the polytropic efficiency. And that's the reason why when we are doing our design, we are taking care of efficiency of individual stage. Okay, that's what we say, we are taking care of our polytropic efficiency. And again, let me repeat, say what I was discussing, whenever you are having conversation with the salesperson, or say maybe those who are supplying you say compressor or maybe your engine, when they are claiming some numbers in sense of efficiency, be careful, as and when required just inquire and check with whether they are talking of overall efficiency of the compressor or polytropic efficiency of the compressor. So when we will move ahead with our design part, that time we will be taking care of polytropic efficiencies. So all stages, let's say like for your engine, you will be having your fan, suppose high bypass ratio engine or low bypass ratio engine. For that you will be having your fan, you will be having your LP spool, you will be having say HP spool, that means LP compressor, HP compressor, maybe if it is a 3-spool configuration, you will be having intermediate pressure compressor. And for all of them, these polytropic efficiencies we need to assume, and there is a systematic way to use these numbers. So we will be discussing in detail how we will be deciding these numbers. So with this, let's move ahead. Say this is what is representing, this is what all we have discussed in sense of our velocity triangle for axial flow compressor. And it says like this is what is say my stator, I will be having my rotor. Okay, and if I will be taking my mid section, I will put my station, say station 1, station 2 and station 3. That's what is representing my condition at stator inlet, stator exit, rotor and intake, and say rotor exit. Okay, now like we have discussed, we will be having 3 components. That's what is say one, we say it is my axial component, that's what is in the direction of my flow, that's what is responsible for my fluid to flow through. So like when I say I am writing my mass flow rate, I used to say my mass flow rate is given by density into area into my axial velocity. Next component, that's what we say, it is my tangential component, and we have realized using our Euler's equation, this tangential component, that's what is responsible for doing your compression work. We are working on our working fluid. Okay, we are having third component, that's what is say perpendicular to this, that's what is representing my radial direction, that means that's what is along my span. Okay, then we have realized how my flow, that's what will be coming out from my stator. Okay, how I will be having my whirl component at the entry of my rotor, what will be my work component at the exit of my rotor. Then we have realized in order to have your work done or the pressurized requirement to be higher, we need to go with increase of our work component at the exit of my rotor. Okay, so this is what all we were discussing. Then we were discussing about the change in velocity component. So here if you look at, this is what is representing my relative velocity component. If you look at the entry of my rotor, my relative velocity component, that's what is higher. At the exit of my rotor, my relative velocity component, that's what is coming to be lower. Okay. So when we say axial flow compressor or say any compression device, for that compressor device, your relative velocity through the rotor, that will be decreasing. That's what is representing the diffusion work, that's what has happened. Okay. Now if you consider say your component of absolute velocity, say at the entry of my rotor, my absolute velocity component, and my exit of my rotor, say absolute velocity component, it is clearly been seen like my absolute velocity at the exit of my rotor will be higher compared to my entry case. Okay. So this is what all will be giving us idea about what all are the velocity components for axial flow compressor. So let me repeat again, we are having our axial flow component, that's what is the axial velocity, which is responsible for my fluid to flow. I am having my absolute velocity component with which my flow that will be entering inside the stator. I will be having my relative velocity component, that's what will be entering to my rotor and will be coming out at the exit. That's what we say relative reference frame components. We are having say whirl component, that's what is responsible for your tangential force and that's what is responsible for your work done. Okay. So now we are clear with this. One more parameter, that's what is your peripheral speed. That is nothing but my rotational speed is correlated with that. We will see today what is the use of this peripheral speed. So peripheral speed, it is mainly been written as a pi into d into n by 60, where d is the diameter or the location where we are doing our calculation, and n, that's what is nothing but the rotational speed of my wheel. Okay. So I am sure this is what all we have discussed in earlier class also. Now let's try to understand how we will be using that for our actual case. Okay. So here again, if you look at, this is what is representing my rotor, this is what is representing my stator. If I will be taking my midsection, let me put here. Okay. Now like in order to have your configuration here, it says I am having my rotor at that midsection, I will be putting this component. Okay. I will be putting that, I will be showing that as my aerofoil. So my flow that will be entering inside the rotor with relative velocity of V1. Here if you look at, this is what is representing my area at the entry of the rotor. This is what is representing the area at the exit of my rotor, and it will be leaving with velocity V2. Do not forget what passage we are making for our rotor or even for stator, that will be having diffusing passage. Okay, and that's what it is reflected at the entry, my area is lower, at the exit my area, that's what is coming to be higher. Okay. Now let's talk in sense of say stator, what is happening. Say this is what is happening in the stator. I say my flow, that's what will be entering with my absolute velocity C2 and it will be coming out with say absolute velocity C3. Okay. Now with this background, I am sure you can make the velocity triangle because we already have discussed about this part. Okay. So let's take your pen and paper and try to plot the velocity triangle for this with this background. Okay. Now let me put this aerofoil. This aerofoil, that's what is representing my rotor, and this is what is, say we are having rotational direction, and as we have discussed, our rotational direction, that's what will be mainly from, if you consider it is from my suction side to the pressure side. Okay. Now like this is what is. Now if we consider, say, my flow, that's what is entering in axial direction, means my entry it is axial. If that's what is your case, you can say this is what is representing my axial entry, and I am having my absolute velocity, that's what is to be same as my axial velocity. Now what we know, this is what is my rotational direction. So if I will be putting, that's what is representing my peripheral speed u. This is what is at the mid section, that's the reason I have written that as a m. Okay. Now as per our velocity triangle law, what all we have discussed, I will be joining that with, say, relative velocity component. Okay. And this angle, now what I am putting, let me put this angle as a beta. Now this beta angle, that's what is defined as a relative air angle. Sometimes people used to say this as a blade angle. Okay. Sometimes they used to say relative blade angle. So do not get confused with this part. So the component of my angle for rotor, that's what we are representing using beta. That's what is a function, that's what is correlating your relative velocity component. Okay. Now at the exit, what will happen? My flow that will be coming out with relative velocity v2. Okay. I know what is my rotational speed u. So I will be putting that as a rotational speed. Okay. And if I will be joining that, that's what will be giving me my absolute velocity component. Now let me show you here. If you look at, I'll be putting my angle. So careful when we are talking about this axial flow machine, we are measuring angle with reference to axial direction. Okay, do not get confused. Universally people, they are measuring these angles in reference with the axial direction. Okay. So these angles what we are measuring, as we discussed for relative velocity component, that's what is I am representing as beta 2. It is nothing but my blade outlet angle or relative blade angle at the outlet. This is what is representing my absolute angle at the exit. Okay. Now what happens? This flow velocity, that's what is, say, c2, with that velocity my flow that will be entering inside my stator. Okay. So let me put this as a stator. Okay. Now at the same way, at the exit I will be putting my angle, that's what is alpha 1 equal to alpha 3. Let me put it here in way, say we are assuming our axial velocity to be constant throughout the stage. Okay. For multi-stage also we are assuming our axial velocity to be constant. At this moment, this is what is my assumption. As we go ahead, I will say my axial velocity will not remain constant. But in order to simplify our problem, we are initially assuming our axial velocity to be constant. So you can see here this axial velocity and this axial velocity, their magnitudes are same. Now let me put here, this is what is my CW2 component, that is nothing but my whirl component. Okay, that's the component, it is component of my absolute velocity. And as we have discussed, this is what is responsible for your compression work to be done. Okay, so this is what is very important. If you recall, when I was discussing about the TS diagram, that time I was talking to you, say when people they are doing design, at the entry absolute velocity and the exit of my stage absolute velocity, that's what they are assuming to be constant or they are assuming to be same. This is what is for ease of making and ease of designing the components or the stages. Okay. So when we are designing multi-stage axial flow compressor, that time in order to make repetitive stages, designers they are preferring to have this absolute velocity at the entry of the stage and absolute velocity at the exit of stage, that's what is to be same. So it says my alpha 3 and alpha 1 they are same. It says my absolute velocity C3 and C1 they both will be same. Okay. Now suppose if I consider I will try to enter my flow not axially, let my flow to enter at some angle. So that's what we are doing. Suppose if I consider my flow, that's what is entering at some angle alpha 1. We are measuring, again I am repeating, we are measuring our angle with reference to axial direction. So this is what is representing my absolute flow angle at the entry. If that's what is your case, my peripheral speed, suppose if I am taking to be same, okay, under that case I will be having my relative velocity component, that's what is coming v1 dash. Now if you compare these two relative velocities, you will realize at the entry my relative velocity, that's what is going to be lower. Okay. Now here in this case the angle what we are measuring with axial direction, that's what we are writing as beta 1 dash. That is also my blade angle, or you can say airflow angle, or relative blade angle, or relative air angle. Okay. So you can see if I am using my flow to be entered at, say, not in axial direction, it will be entering at some angle, my beta 1 angle, that's what is going to be reduced. My relative velocity component, that's what is going to be reduced. Okay. And in order to achieve that part, we need to incorporate a component in this stage. Okay. So let me introduce that component. This is what is defined as, say, inlet guide vane. Okay. So what it will be doing here, if you look at my flow that will be entering at some angle alpha 1, that's what is contributing some swirl component. Okay. So here I will be having entry swirl component as CW1. Okay. So when I am incorporating this my flow to be enter in the stage at some angle, basically I am reducing my relative velocity and I am introducing my swirl component. Okay. So we will be discussing all this in detail very soon, why we are incorporating inlet guide vane. If you recall, in introduction session I was talking, saying like on both the sides of Pacific, people they are having different thought process for incorporating the inlet guide vanes. Some of them they say it is of no use, some of them they are preferring to use the inlet guide vane. Okay. So we will be discussing all this in detail. Okay. So now you can understand this is what is representing my velocity triangle at mid section. Okay. Now what we realize, say my rotor, stator, my inlet guide vane, all these components they are made up of number of stations. So you know I will be dividing my span, this is what is called span or the height of the blade, I will be dividing into number of stations. Now let's see what is the use of that. Okay. Now here if you look at, this is what is representing my mid section. Okay. And as I told, we are making this in number of stages. So let me put this as a, this is what is my tip section. Okay. Let me put it here. Say at tip section what is happening, you can see my radius. Okay. My radius, that's what is going to increase when I am moving towards the tip. What is the meaning of that? We know our peripheral speed we are writing as pi into d into n by 60. Now that d is nothing but the diameter. So up till now what we were discussing, that's what was only up to mid section. Now when I am going for the tip, I know my tip diameter, that's what is going to increase. If that's what is your case, you can see I am having my peripheral speed for this rotor, that's what is to be large. If I consider my flow is entering axially only, so this is what is my axial component. If we connect this, that's what is representing my relative velocity component. And you can see my angle. Okay, here what is my angle at the entry of my rotor, that's what is coming to be larger compared to what we have seen at the mid section. Okay. Now let me take, say, at the exit of rotor what is happening. So here in this case this is what is say my tip section, and this is what is representing my peripheral speed. Okay, and if I'll be connecting that, you will see my relative velocity, that's what is coming out from my rotor, that also will be larger near the tip region. Okay, now this angle beta 2 dash also, if you are calculating, that number is coming large. Okay, so what it says, like my work done we have discussed, that's what is mainly been depend on my peripheral speed. When I say peripheral speed, that's what is changing. Basically, that's what is changing my delta beta. That is nothing but my flow deflection angle. Okay, so near the tip region, you will be having your delta beta to be coming to be large. Okay, now suppose if I consider the next station, suppose if I am considering this is what is say my hub. What we know, my hub diameter, that's what is coming to be lower. Let me put in this case, say this is what is representing my hub peripheral speed. Okay, now if I will be connecting, surprisingly you will see my relative velocity component, that's what is coming to be lower. Okay, and if I look at my angle also is coming to be lower. Okay, in line to that, what will happen at the exit? Let me put this my U hub, that's what is I am representing by the small component. It is pi into diameter of hub into speed by 60. Okay, and this is what is representing my blade angle. Okay, now this is what is making your fundamental understanding for blade. Now people used to say, or the blades what you have observed for the compressor, these blades are twisted blade. Okay, so it is not that people they are making that blade twist. Okay, this is what is geometry, that's what is insisting you to make that blade to be twisted blade. Why it is twisted? You can see my angle, that's what is varying from beta 1 double dash at the entry to beta 1 dash at the tip. Okay, same way at the exit, I will be having my variation of angle beta 2 double dash to beta 2 dash at the tip region. Okay, now you can see here what we have done, we have divided whole our aerofoil in number of stations. Now when I say number of station, I will be having radius at each station. Okay, now at each station I will be having my peripheral speed. If I am considering my axial velocity to be constant, you can make number of velocity triangles. You can make calculation of your variation of beta 1. You can make variation of your variation of say angle beta 2. Okay, so this is what is representing how my angles, that's what is varying from hub to tip. Okay, similar thing, that's what you will be getting at stator also. Okay, so this is what is very fundamental, and that's what is required by you people in order to move forward. Okay, and I'm sure you will get in detail what all that's what is happening here. Okay, now let me try to explain what all we have learned from your basic Euler's equation. When I say my Euler's equation, specific work done, that's what we are representing as a U into Cw2 minus Cw1. Now if I am using this velocity triangle, then you can say my Cw2, that's what is I am representing as a Ca tan alpha 2, and Cw1, that's what is say Ca tan alpha 1. Okay, now this is what is representing my specific work done in terms of alpha 1 and alpha 2. If you use your pen and paper and if you try to derive the relation, you will get this equation U1 by Ca1, that's what is equal to tan alpha 1 plus tan beta 1, U2 by Ca2, that's what is tan alpha 2 plus tan beta 2. Okay, now here in this case, intentionally I have written U1 by Ca1 and U2 by Ca2. Okay, suppose if I consider here, if you look at, this is what is representing one of my stage. Okay, for this stage, my area, entry area and exit area, that's what is coming to be same. Okay, both the area, that's what is coming to be same. So at any station, my radius will remains constant. Okay, so that's the reason why you can write down u1 equal to u2. But here if you look at, say this is what is representing my fan. And for fan, if you look at, my entry area and exit area, that's what is coming to be different. Why? Because I will be having the rise of pressure. When I say rise of pressure, at the exit you will be having rise in density. And according to our continuity, my continuity at entry and exit must be satisfied. So in order to accommodate the rise of your density, my area, that's what will be coming to be lower. Okay. Same way, if I consider this is what is representing, say, my HP spool or HP compressor. Now for this HP compressor, if you look at, this is what is having systematic shape, which we can assume that as a constant half diameter configuration. Again, you are having the change in your radius. Okay, and that's the reason why, let me go back, that's the reason why we are having this to be, for high speed or high pressure ratio configuration, my R1 and R2, they will not be same. Okay, and if we are assuming our flow to be axial one, it is not accelerating or decelerating, we can say my U1 by CA1 equal to U2 by CA2. And that's what will be giving me very important equation, that's what is called aerodynamic work. We can represent that as a U CA 10 beta 1 minus 10 beta 2 kilojoule per kg of air. Okay, I can write down W over m dot, that's what will be representing my specific work done. Do not get confused with this term. Okay, so you can say my aerodynamic work, that's what is a function of my peripheral speed, that's what is a function of my axial speed, and my angles beta 1 and beta 2. We will be discussing in detail in next lecture what all is a use of this equation. And this is what all we have learned from our basic understanding. It says this is what is, say, my thermodynamic work, that's what is m dot Cp into delta T0. That's what is representing in sense of kilowatt. Okay, so here we are stopping with, this is what is giving us all idea what all we have learned in sense of our velocity triangle and what we have learned about Euler's equation and its application for the calculation of work done. Thank you.